All right, welcome back for day 10 of Advent of Code. If you're still sticking with it, congratulations. A lot of people usually fall off by now. I think by the numbers, we're saying about 220K started and about 40, 50K did yesterday. So if you're still on it, good on you. There are, however, more than halfway still to go. So if you're feeling a little tired, make sure you take the time and space that you need to get through all of this. So we are on day 10, lava production facility, topographic map, height at each position. This is starting to sound a little bit like pathfinding based on unscorched scraps of the book. We're looking for as long as possible and an even gradual uphill slope. A hiking trail is any path that starts at 0, ends at 9, and always increases 1 each step. No diagonals, only north, south, east, west. A trailhead is any position that starts with one or more hiking trails, so all positions of 0. A trailhead score is the number of 9 height positions reachable from that trailhead via a hiking trail. In the above example, the single trailhead in the top left corner has a score of 1 because it can only reach a single 9. So it's not the number of paths that can get to this 9, it is just the number of 9s that are reachable from this starting position. I think we only increase, so the restrictions are pretty high, which is probably good. Okay, larger example has 9 trailheads, so 9 zeros. Considering the trailheads in reading order, they have scores of 5, 6, 5, 3, 1, 3, 5, 3, and 5. I don't know what reading order is. Maybe that's top down, left, right. So this is 36. The original example is somewhat unuseful, I think, because there's only one that we can get to. So I think we have to start with the larger one anyway. What is the sum of the scores of all trailheads in the map? So we'll just create day 10. Get into part 1, make sure our test runs has the input. I think it was 36 was the right answer. So check 36. So the count is all of the places that each 0 can get to. So all of the 9s, right? I think we'll start out simply with this. We can, and I have in the past, I'll make this a little bit bigger too. We can, and I have in the past, use fancier crates. There are 2 crates in particular that are pretty good for problems like this. One is called pathfinding, and it has a bunch of algorithms. This is the one that people usually use for Advent of Code. Its usability, or like the developer experience of using the APIs to do the algorithms, is a little bit different than the other option, which would be petgraph, which also comes with the ability to traverse a graph in a number of different ways and comes with a number of built-in algorithms. I don't think that we need either of them right now. So I think what we're going to start out with is a fairly straightforward recursion approach or something like that. I think we can do a breadth first search, and we can probably keep track of all positions that are reachable, and then at the end count how many of those positions are 9. So one of the questions here is, how do we want to get this information? We have effectively already written these parsers before. I think day 8. So on top of that, all we really need to do for day 10 is make sure that those dependencies are still in our tree. So let's glam and nom locate in this case. Again, you don't have to use glam like I do here. You could use tuples. You could use whatever you want. I find it significantly easier to work with ivec2s because it keeps track of which is the X and which is the Y for me. You could write your own struct that's lightweight that does the same thing. You could use tuples. You could do this. However you want to store this is perfectly fine. I use ivec2s in these problems for clarity, for my own clarity, so that I don't start mixing up which of these X and Y values is in what order at what point in my processing. So we have the parser from day 8 in here, et cetera, et cetera. I forget what the input was for day 8. I think it was still this grid. Yeah. So we do have a little bit of change to make to this parser because we're actually just going to take everything, honestly, right? This whole preceded thing, we can leave because technically there's new lines. We could also turn this into a separated list, right? If we do a separated list, we are separated by line endings, and then we have to get all of the individual characters themselves. So this could be something like many1 alpha num position, which is what we named the parser from day 8. We do need to keep something here. So we have a separated list, right, which is a vec. And because of the way we just rewrote this parser, we end up with a vec of vecs of positions and characters. I think we want the numbers, right? It's always 0 through 9. So we can make sure that we convert those. We don't need this to be alphanum anymore, right? So we could switch it to something like is numeric and run this 2-digit with a radix of 10 and unwrap this because it will always succeed. That will turn this into a U32, I think. No method named unwrap for type bool. Is digit is not what I want. I want 2-digit. So at that point, we get this U32. I think U32 is good because these digits are never going to get added together. We always just increase one, so U32 is fine. They could actually be U8s even, or something like that. So in this case, we would get U32s here. And I think that we probably want to take this input. So I'll split this out like this. Input, I'll just call this lines or something like that. Use our question mark here. Save to get a little bit better formatting. And now we have a vec of vex. So if we wanted to, we could have done this in a fold. We could have put these in a little bit smoother, but we can also do lines, iter, flatten, collect, hash map ivec to U32. We do need to pull in hash map here. That's from standard collections. So I'll call this hash map. I typed map here while I was thinking out loud earlier. We're not going to use a map there. So one of the issues here is that we have references to that data now. We have a reference to the tuple. So we can stick .cloned in here. Also .copied works. Both of those are valid in this case. Cloned and copied are basically a lightweight and a heavyweight way to copy things. Some things implement copy, some things implement clone. So we can return input hash map here instead. And now we've got a hash map of ivec2s to u32s. So we should see that in our result here if everything is going well. And now we have, let's see, 4, 7 is a 6. So 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5, 6, 7. That's this 6. So, I mean, if we got that number correct, we probably got a lot of other numbers correct. So we have a hash map, which is nice because we're going to be doing a lot of like ivec2 based access to run this algorithm. Of course, we don't use the input past this point, so we're just going to underscore that. I think I'm just going to call this map. So we do map.iter.filter. Filter is going to give us a tuple here of the key and the value. So the position effectively and the height, I believe is what these are. We need to find height equals 0. That will give us all of the positions that we can start at. And then I guess we can map over this. What do we need to count? We need to count the number of 9s that are reachable. So we need to transform this from a starting position into, I guess, all of the positions that we've seen for each of those starting positions. I feel like we could have maybe 2 hash sets here. One for all the places we've visited already, and one for the places that we have newly visited. That could make the looping a little bit easier. And then we're just kind of doing a lot of like hash set checks. We could also just have one data structure, like one hash map that had positional values and an optional value for whether that was already checked or not. Again, we don't really need the path right now. I don't know if we're going to need that in part 2. I'm just going to call this counts for now. The height is a double reference to a U32, so we can definitely use that in our filter. I'm going to throw an underscore in there. And then we kind of just loop here. I think that we set up maybe a visited hash set of ivec2s, which I guess would include the starting position. Oh, I probably just kicked us off into a loop here again. This is like the 4th time I've done that? Oh, we didn't pass. We didn't run yet. I did not. Let's make sure that we just have a break in here before I infinite loop us again, which I have done multiple times before. So from reference of ivec2 is not available. We do kind of want the, oh, right, because this actually needs to be an array for the hash set to be created. And actually, this isn't going to go in visited now that I think about it. So we end up with visited, which are the, I guess, places that we don't need to process anymore, and the places that we do need to process potentially. We do need north, south, east, and west, which we have as ivec constants, associated constants, that is. So in this loop, we need to take the new locations, I guess check each of the 4 locations. So I guess let's start by checking 1. So we basically end up with this array, which we could stick in a constant up here too. But I feel like, well, there is axes in the constants, but there is no result that gets us all the positives and negatives. So we can do our own here, right? And then we've got this constant that is this set of 4 directions that we need to add in each And we'll just fetch the location value, which always has to exist, right? So that's our current height. And then we have to map over each of these directions, add it to the location, then filter for locations that aren't in visited, right? So not visited dot contains new location. And I guess it doesn't matter if it's already in the hash set, but we can avoid some processing. So new locations. So in this case, we filter, use after move due to implicit call to into iter because of this. So if we iter with a for loop without calling .iter, we're effectively calling .into iter, which isn't strictly required to take ownership, but quite often does take ownership. So .iter will iterate over references, and .into iter will typically iterate over own data. So in this case, we have a position, we take the directions that we need to go in, we map that into each of the 4 cardinal directions, we filter to check to see if any of these locations is a new location that we can visit. If not, then we don't use it. And I think we just collect this into a hash set of IVEC2s. Maybe one more condition here. Let's name these conditions too. So if it's not in visited and it's not in new locations and map.get new location dot is some, and we'll call this h, and we'll do it h equals current height plus 1, and our references probably don't match up here, so let's check that out. There's an issue here with us not using the return of this value, and this is a hash set for each of the new locations that we went through. So really we're just constructing this set of new locations, right? So we'll take the new locations that we've processed and we'll shove them into visited since we're done with them, and we'll reset new locations to be this new hash set, but not this hash set specifically. I actually want to turn this into a map, say this is a new location. This takes us down to here. And then I think if we collect this into a hash set, it will combine them. But it is possible that that is not true. So let's take a look at this with the return value here. We need to fix a couple of reference issues. So the iterator item here is a shared reference to an IVEC2. So that's dir. It also looks like hash set IVEX cannot be built from hash sets. So that's okay too. We don't need to collect the inner hash set. This feels weird. I shouldn't have called this new location. I'm just going to call this location, I guess. That feels right. I think that was the right name for it. I think I renamed it away from what I had before. So we can't use the hash set inner here, but that's fine because we've filtered down to everything that should be valid anyway. So we theoretically can do that and then flatten and collect, I think. Some of these seem to want moves to take ownership. The issue being that new location may outlive borrowed value current height being here. This is a reference to a U32, which, honestly kind of feels weird. Dir may outlive value location, dir plus location. Location here also going to be a reference. If we turn that into an actual value, that's fine for us. And then for filter, new location may outlive borrowed value current height being used later on down here. So theoretically, we don't actually need to do that up there. But if we just move that down there, then closure may outlive the current function, but it borrows the location, which is owned by the current function. This is a reference to an IVEC2. So I actually don't care that much about what we do here specifically for like cloning and stuff like that. So with all of these positions, that should be our new locations. We have visited. Hash sets contain a number of useful functions like, for example, difference, which we don't need right now, as well as insert, which we could use to insert these values one by one, or we could do union here. And then for counts, we need to turn this into, we're already mapping over each of the starting positions. I think we need to write our break condition for this loop too. So if new locations dot length, or rather not dot length dot is empty, I think would be the right move. Then we break. I'm realizing now that we actually had the height available to us. I think that's just the original height though. So we did need to use the one that we were getting. This is a map. This loops over. This fills up these. So what do we want? We probably want visited, right? And probably it's visited.iter.filter map.get position. These should also be valid positions. So I think we can unwrap and then we can count that, right? And then if we look at the typing of counts, we have an iterator of U sizes. So I think we sum this. I think that's what we're supposed to do anyway, because it's the count of all the 9s that a 0 can reach. So that is 36. And I will say, okay, counts.toString. And this is passing now. So we'll do day 10, part 1. We'll get a number. Hopefully this number is correct as usual. And we have a gold star. So that was part 1. So let's toss some of these unused imports and cover what we did. So the whole thing is we have a bunch of positions with numbers. The numbers need to go from 0 to 9 as we move up this trail. So 0, then 1, then 2, then 3, all the way up to 9. And we have to count the number of 9s that we can reach from any given trailhead. So we already wrote a parser that was basically like this in day 8. So I think I'm going to skip the parsing explanation because we've already covered that, which means that we end up with a hash map here of all the positions. So here we take that map and we filter to find all the positions that have a height of 0, which are all of our starting positions. Once we have our starting positions, we can map over them. And this function here could probably get broken out into a different function, I think. Right, so this whole thing becomes a function that is search trail, takes a position, which is an IVEC2, and a height, which is a U32, and returns, I think, a U size is what it returns here. I think this also has to accept the map. So let's do map is a hash map of IVEC2s to U32s, I think they are. Then this function becomes search trail, map, which I'm going to pass in as a reference here, position and height. Now, I think the height doesn't actually matter. We don't actually use it, just making sure this still returns us the right answer. So now we've got search trail. Search trail takes a map of positions, a starting position. Starting position is always 0. And when we're doing our calculations in here, we actually have to get those locations ourselves at some point anyway, because the current height is the current height for this loop, not the current height in total. So we always have to, from this new locations array, get the heights at those locations. So actually, I'm just going to get rid of that height entirely, and we'll just underscore it here and not use it when we pass in the function, which cleans this up a little bit. So now we're searching the trail, given the map and the starting position. So this is one trail from 0. We create a vec of visited nodes, which is this hash set, and we create a hash set of visited positions and a hash set of new locations. We do a hash set in this location because there's really no reason for us to keep duplicates. So we can set that assumption up from the beginning. We have to loop over all of the new locations. In this case, we start off with just the starting location, which is, I don't know, we'll say 4-3 or something like that. At any point in this loop, if the new locations is empty, then we're done. We have no locations to check anymore. And otherwise, we do this increasingly breadth first search on all fronts by taking this number of new locations, iterating over them. I actually have an extra clone in there that I can get rid of. I wonder if Clippy can give us anything. So an errant clone in there that we didn't need, I just got rid of that by using cargo Clippy, checking, and just making those changes. So we've got new locations, we're iterating over them. Each of these is a position at which we could currently be, and we're naively checking for all 4 directions, even though we would have just come from one, because that means we can kind of fully parallelize this if we want to. We can just keep checking all of these locations, keep looking at stuff in the map, and it doesn't matter where we came from because we can only go up, right? So we can only go from 5 to 6 or 1 to 2. So we take whatever location we happen to be standing on and we look for all 4 directions around it, which in this case, I decided to zip those 4 directions with the original starting location so that when we were mapping here, this map would be self-contained and we would have the direction we need to go and the original location, which we also keep around. So we end up filtering the new location, so the set of north, south, east, west locations from where we're currently standing, by checking to see if it's in the visited hash set, checking to see if it's in the new locations hash set, because if it's in either of those, then we don't need to put it anywhere. We don't need to do anything with it. We can just not drop it right there. And if it's in map, which it should be at this point, then we can take the current height that we're standing on and check to see if it's a valid location to move to. If it is, then at the very end, we just do a little map here to drop the original location and keep the new location. That gets returned from this flat map, which we collect into a hash set. We then replace visited with the union of visited and the locations we just generated for all positions that we were standing on, all places we could go next. Now this does give us references, so I used .cloned here to create the hash set of ivec2s that I wanted. So visited is the full set of everything we've been to already, and new locations is all of our new locations that we're now standing on. And then we loop over this again and again and again until new locations is empty, at which point we take visited, we iterate over all of the places we've been, we look for any place that is a 9 and we count the number of them, and that is the number that we need to return from this function that we then need to sum. Now, part 2 is different. Part 2 requires keeping track of all of the valid paths. So I actually think we're going to get a different implementation here. So let's start by taking part 1 and dumping it into part 2. No real reason not to. The answer here is going to be 81 instead of 36. I actually don't think we're going to keep any of the logic that we had. We do early termination in our current code, so we would have to keep around those positions again if we wanted to keep track of all possible paths. And then we would have to keep count of a number every time we branched. So this might be a good time to use pathfinding, the crate. There's one called count paths here, which counts the total number of possible paths to reach a destination. No loops, which we don't have. So if we read the docs, it says count paths takes a start, which is some t value, successors, which is fn, so some function, and success fs. Now we would need to run this multiple times. So we theoretically could run part 1, find all the 9s that we can reach, then run this for each of those destinations. So in that case, if we are going to pull back our search trail function and we want all of the positions with 9 rather than the count, we can just remove that. I really don't mind collecting here. We're going to end up with all of the locations. So like a vec of ivec2s. We could also impl iterator item equals ivec2 not collect here, but I really don't generally care about doing like an iterator return from this. So we'll end up with the vec of ivec2s. This is all of the positions for this position, starting position, that it can reach, which is interesting. Because then we can map here, we can say, here's the starting position, here's all the 9s that we can reach. Then we've got starting position and ending positions. What do we actually need to calculate here? The sum of all the trailhead ratings. So a rating is the number of distinct hiking trails which begin at that trailhead. So the sum of all of the ways to get from 0 to any 9. So we don't have pathfinding in right now. We do need to grab it. I don't remember if I kept it around. No, I didn't. So we'll use 4.11 here. We need to bring count paths in. We get a huge bundle of errors, which we can make go away with a simple to do, I think. I think we also need to sum here anyway. So instead of to do, I'm going to put 0 here so that we compile, we get pathfinding. We've got the starting position and all of the ending positions. So we need to do this in a loop. So the start, how do we get the successors? And then the success criteria. So the position effectively. So we're going to start from starting position. We are going to get that and do something to it and check to see if this is equal to the ending position at some point. And we just need the first part of this, but we also need this filter. So we actually need this whole chunk for a given starting location. So this will give us an ivec2 double shared reference. We get our directions that we talked about earlier. I think that this starting location needs to be our position here. This is checking to see visited and new locations, which neither of which we need. So we can get rid of those. We only need to know if these 4 locations are valid. And the only reason we need to do that is this map. And then starting position is a shared reference. So we're going to make that an actual ivec2, which will fix our issue. And then this ending position is going to come from ending positions dot iter dot map, I suppose. Ending position, open it up here. This closes here. So we've got our ending positions. We iterate over them. We map. We get an ending position. We count the paths from a starting position to some ending position. In this case, this is a reference to an ivec2. Down here, we get an ivec2. We can use both of those references to compare them here. This returns us a number for this starting position and that ending position. So we actually need to sum this up and return it, which then gets summed over everything. I think this isn't typed. So instead of going all the way up and kind of separating the type from the location, I think we can do this here. We change, right, this needs to be returned. And then it looks like our test passed. So let's check that. We end up getting a correct output here. I need to turn off links in my terminal. I click links all the time and I never mean to. So let's do cargo run part 2. This runs, gives us 1210. And that is the answer for part 2. So we're done. Huzzah. Now, I especially like right in here with this zip and some other things like that, especially with this map filter map situation going on here. I also nested things quite a bit. I think that all of those are valid refactoring points, right? Even this like count paths could get factored out into a different function. So then we would search trail and then we would rate trail. So let's pull this out just to start out with, and we'll call this rate trail. And we're going to sum out of this. So this is just going to return the number. I do think we need the map and the starting position and ending positions. So if we do fn rate trail, dump this in here, we're going to return a usize. And otherwise, this is going to look very similar to the type signature we have for search trail. So we've got a map, a hash map, shared reference to a hash map specifically, because we kind of construct this map at the beginning and then never get rid of it. We never do anything to it. We don't even mutate it. We just kind of keep it around forever. We get a position, which is, I think the starting position is what we need here. And we need ending position. And we'll say this takes a slice of IVEC2s. So we end up with a vec of IVEC2s here. A slice overall seems to be working out for us. So we can just add a shared reference here and it will deref to this slice. The other option here was to do like something like a vec like this. There are trade-offs between doing the two of them. In general, I like doing slices because that applies to more containers, but this is fine as well. Also, this code right here, the little piece that does like the successors, so to speak, we do at least 2 times. So we do that when we're searching the trail here and we do that up here. Slightly different logic for the filter, but we could, remove that and add it as another filter. So we could probably take most of this and pull it out into another function, cleaning this up even a little bit more, and so on and so forth. Let's make sure that we get our answer here after I did that little refactor. So 1210. And what we end up with is our map iterated over. This is the entire map. We look for all the starting positions. We take those starting positions and we do a search for all the ending positions, all the 9s. We covered this in part 1. And then we map over it again with those starting position and ending positions. And we rate the trail using the map, the starting position, and the end positions. We do that with a function called count paths. So we take all the ending positions, we start at the starting position, and for each of those ending positions, we have to determine what is a valid tile to go to next. We do that in the same way we did that in part 1. So this is a copy and paste of the logic that basically looks at each north, south, east, west and determines if that height is a valid height to go to. This all gets returned, and this is our ending check. So if we are on the ending position, then we're done. And count paths handles the heavy lifting for us. And we get a sum of all of the paths to get to the end. And we sum that up as a usize, and we sum it up again for every starting position, which is great. Let's take a look at our benchmarks at least. I don't know what they're going to be like. I feel like 1 millisecond, 2 milliseconds, we could probably get these down. That feels long. We basically implemented strongly connected component here by ourselves, and we've roughly doubled the time here in our execution. So maybe our implementation for part 1 could use strongly connected component instead. So for part 1 refactoring, we'll do part 1 pathfinding. I think I've set up the library, the bin, the benchmark, part 1 pathfinding, and strongly connected component takes a node and the function for successors. So that's basically search trail. So let's do fn search trail again, and we'll copy our function signature. Strongly connected component takes the starting position. I think we also need to pull this in because I didn't bring it in before. Great. And then we need the function that returns the valid next positions, which I think we'll yoink from part 2. So that's this right here. We'll dump that in there, and this is not going to be our return value. I think this is going to give us an iterator of all the components. So I think we do our filter again. I think we have the filter here. This is the filter, and then we need to count that. Something wrong with the filter. So what does strongly connected components actually give us at the end? It gives us a vec directly. So this is not an iterator. Strongly connected component. Oh, that's a single. We need strongly connected components, but really we want strongly connected components from, because we're going to go from this start with those successors. So let's do this instead of that and change our import to star for the prelude from pathfinding. This is also a function. So we'll do pause here, I think, and that gets us correct. And then we would need to like into iter here to turn this into an iterator again. This would be a shared reference for the map. Maybe I was wrong about that. What is pause here? Pause is a vec of ivec2s. So let's do this instead. Let components equals this. I think we're only going to get one out of this. So let's find out if I'm correct or not. We'll debug components, and ideally this runs and gives us what looks like a bunch of sets of components. Now the question is components into iter.flatten.filter.count, and hopefully that's the right answer. 531 is the right answer. So for our use case, because we're doing this in the right way, this gives us the right answer. Let's do a bench on 10 and see if that changed our runtime. And it really didn't. So let's make sure that I did this correctly. Nope, pathfinding. Make sure your benchmarks are actually benchmarking what you think they are. Okay, we still didn't change that much. We changed by 300ths of a millisecond, which I'm honestly pretty happy about in terms of like manual implementation versus the pathfinding one. I think we can get rid of this search trails function, or at least the old one, right? And then probably also worth benching the parser today just for kicks. So we'll set that up and run this again. Hopefully our parsing isn't like massive amounts. Yeah, so our parsing is 140 microseconds, which means it's not really that much of our runtime. I'm curious to see what numbers other people got. I'm sure there's an algorithmic shortcut of some kind, but we did ours very straightforwardly. We could do rayon. So do we have rayon installed? I think it's in the workspace. So go back into our part 1 pathfinding _ rayon, and let's just go to rayon. We'll check the docs. So we can see that by throwing par iter on our iterator before our filter, actually, we drop down to 300 microseconds. So this is at least partially just because we're doing so much pathfinding that is parallelizable. So a couple different things today. I feel like I'm reasonably happy that our pathfinding versus our regular implementation aren't that far off. I'm sure that I could do my manual implementation better. And perhaps there's an algorithmic trick that would speed all of this up in the first place. And there's almost certainly also things we could have done. But I'm generally happy with this. We got the right answers again for part 1 and part 2. So if you have any questions, as usual, leave them in the comments, and I'll catch you in the next one. Let me know how you did today.